after you generate so many microstates and you plot them, this is what you will be seeing. So, here I am just showing a couple of properties of my molecule of interest. My molecule was a biomolecule, a protein. So, if I plot the potential energy of my system over time. So, this data are generated from molecular dynamics simulations, and therefore, there is a time involved. So, if I plot over time, I see how my potential energy of the system is varying. So, the potential energy was minus 1.605 10 to the power 5 kilocalorie per mole, and over time you can see the potential energy is decreasing. So, that means the system is stabilizing further when I when I generate more and more conformations. Here I am showing the free energy of binding of a small ligand into the protein, and I generated different conformations of the complex and calculating delta G over time. Here I am showing basically something called root mean square displacement. What is the deviation of my new conformations compared to my starting conformation. So, I started from conformation, let us say unfolded protein, and now I am trying to see the protein folding, and when I get the new conformations, I can compare those new conformations with respect to my starting conformation, and I see how much I have deviated from the starting structure, and this RMSD is basically showing how the molecule has evolved over time. So, if you plot them up over time, you basically see every microstructure. So, here each point here like it is more easily visible. So, here each point is basically showing the structure of the protein ligand complex. Now, if you want to get the average over all these energy values, or you want to get the average potential energy of the system, you can go back to your definition of ensemble average or time average, and you get those properties calculated. So, we will do that now. So, like how you calculate the average property, we have discussed how we calculate the average property. So, I will just take a couple of examples, like if you want to, so you simulated your system and you generated several microstates, and now I am asking you to calculate the average potential energy of the system. So, how will you calculate? You can calculate the ensemble average, and so ensemble average of that would be, since I am taking the time average, so m is number of microstates I have generated, and I is equal to 1 to m and ui. So, ui is basically energy of ith microstates. So, if I take the average over all the microstates generated, I get the ensemble average. If I have to calculate the ensemble average of the kinetic energy, let us say K is my kinetic energy. So, how am I going to get that? So, again I will take the time average. So, my m is number of microstates generated, J is equal to 1 to m, and then I have number of particle n, and my kinetic energy is nothing but half mi vi square. So, that is for 1 microstate, and if I take the average over all microstates, I get the kinetic energy. So 1 by m j is equal to 1 to m, I is equal to 1 to n half mi vi square. So this is the ensemble average of the kinetic energy of my system. So here I have summed over all the microstates and then divided by number of microstates, and that is the average value. And here I summed over all the n particles present in my box in each microstates. So that is how you can calculate the average kinetic energy. You also can calculate RMS deviation between two structures. So what is the root mean square deviation between two configurations, between two conformations? Let's say my conformations are alpha and beta, and so I am talking about root mean square. So RMS is taking the average. So alpha is my state and beta is my another state, and I want to get the root mean square. Root mean square. So I want to get root mean square deviation between the alpha state and the beta state. So that's my RMS which I want to calculate. And so if I have to get it, I again have to make use of my time average, and again 1 by m, where m is my number of microstates, and I is equal to 1 to m Ri alpha minus Ri beta to the power square. So that's my root mean. By mean is this ensemble average. So root mean square displacement between two states alpha and beta can be obtained from your set of microstates generated from molecular dynamics or Monte Carlo. Okay, then next thing, okay, let's take one example, one test case, how my ensemble average values compare with the experimental data. So